times lecture 20. So this is about lecture 20, and I go, he said. Welcome to video number 20 in biomechanics.
Now this is the second video in section 7, and we're going to be starting part B here, where we look more closely at flows around immersed bodies. And specifically what we're going to be looking at is drag. And so drag is the force that impedes, that is pulling back against the direction of motion. And so that's what we're going to be looking mostly at in this video here. Okay, so this is the breakdown of section 7 with what we're covering shown in the white text. So you can see we're starting part B here, looking at the fluid flow around immersed bodies. And in this video, we're going to do drag. And that's broken down into these 4 subsections that you see here. So in part B here, now that we understand what boundary layers are and we understand what separation is, we want to know what are the effects of that. So because we have viscous forces around these bodies, there's going to be, for example, some drag on them, right? There's going to be some shear. There's also going to be the normal surface forces, right, which are the pressure surface forces. So the tangential ones are the shear ones, the normal ones are the pressure forces. So we're going to have, because of the flow, we're going to have the shear and we're going to have the pressure forces, right? So this is going to be one of the ways we break down part B here. So when you have fluid forces flowing around an object and you break that down, we tend to break that down in terms of drag and lift, where we have drag being the direction that the object is moving, right? Or the same direction that the flow is passing over the vehicle or object. And lift is the forces normal to the flow direction, where when we speak about lift, that's calibrated upwards, because generally we're counterbalancing gravity forces there. So I'll show a video here, and we can take a look in this video to see generally what the flow over these objects looks like. And then again, to inform us, so what is it we're going to be looking for in part B here when we do these calculations, when we try to understand how to design things, knowing how the fluid forces are going to act on these objects. Okay, so I'm going to push play on this video here and then chat about a few things we can look at. So it's comparing an old Model A versus a sports car. And because of the smoke tracers there, we can see the flow over each vehicle. We see that the sports car is more streamlined, so it has a smaller wake at the back. I'll play the video and point to these things. So the wake is much larger back here on the Model A versus the sports car. The wake is much smaller. So this wake is much larger, so separation here and here versus the sports car, the separation is occurring closer together, so there's a smaller wake there. And so we know that from the fluid flowing over the vehicle, there's going to be some drag, right? So I'll just kind of label this beside it here. So when we say drag, so that way is drag in this video, and lift is like straight up in this video, so I'll throw it back on here. Okay, so in the drag direction, we basically have the drag from the friction of this flow here. We have some pressure drag from hitting the front of the vehicle, and then this wake region, there's going to be pressure drag pulling back as well, right? So we're seeing already, we're breaking it out into friction and pressure drag. And then the lift, right? So we saw on an airfoil, anytime we increase the velocity, so if you have this streamline here, and if this velocity is faster, for example, than this velocity here, you're going to get a pressure difference, and that's going to generate this lift, right, in the upwards direction. And so there's quite a bit going on here. So the first section we're going to look at is just the drag direction, so in this flow direction. And then we're going to break that out into this pressure drag, right? So these normal forces, there's pressure drag here. And then there's also the shear of the flow along the car causing the friction drag. So that's a video there that motivates what we're looking at here. Now, I'll point out that as we begin this, we've already talked about drag in the past and seen that generally after you do something like a dimensional analysis, you need experiments, right? So you generally need to generate a plot to be able to calculate the drag force. And so we note that a lot of what's going to be providing the data for calculations in part B here is experimental methods. Also some advanced CFD. Now that computers are becoming more powerful, we have a better shot at solving things like the Navier-Stokes equation numerically. But for the most part, it's experimental still at this stage. So in the drag section here, some kind of note that like we are parallel to the direction of motion. So we've basically grouped this from like a Buckingham pi from a dimensional analysis. You've got your drag force coefficient and your Reynolds number. And that's the only thing that this 2 is a function of. So drag force grouping and your Reynolds grouping. And then, as we talked about previously but didn't really look at in detail, we have the drag coefficient. So we define this, so that's why there's a triple equal sign saying is defined as this grouping right here. So we take this grouping, we actually only add this half here because now it becomes the same as the dynamic pressure term, the half rho v squared. And then so when we write drag coefficient, what we're looking at then is this dimensionless grouping. So the drag coefficient is really the dimensionless drag force. So then we just have two things, right? We have drag coefficient is some function of the Reynolds number. And this is for a sphere, smooth sphere we saw this for. Okay, now that drag force, as I just discussed in looking at the video, right? The drag force can really be a result of the tangential forces, right? The shear of the fluid flowing over the vehicle in the direction parallel to motion. And it can also be from the pressure, the normal forces. So we'll look at those two separately. We're first going to take a look at pure friction drag. So in the pure friction drag, we consider the case of a flat plate that's parallel to the flow. So basically you have some flat plate like this. It's parallel to the flow, so you have some velocity profile like this before it hits the plate. And then you have sort of some boundary layer growth right here. But you don't really have, so this distance right here is actually so small, you don't consider any of these normal forces to be acting on the flat plate. You just consider the shear over the surface of the plate due to these viscous effects right there. So then that's what we say here. We say the drag force is just a function of the wall shear stress. That's it. We don't consider any pressure drag at all. So we're pure friction drag right now. And then a lot of these are experimentally determined. So some of the laminar ones are based in analytical calculations, but for the most part, these are experimentally determined anyways. And so that's a laminar one. That's a turbulent one. Generally speaking, they also come with like ranges that they're applicable for. So this one, for example, 5 times 10 to the 5 is your Reynolds, and the L there denotes the full length of the plate. So we write that L there. That's as opposed to the X one, which was a local Reynolds number. So that's just distinguishing between those. So that one's good for between 5 times 10 to the 5 and 10 to the 7 for Reynolds number. This guy down here is generally Reynolds less than 10 to the 9. So that's because, right, this turbulent expression here goes to 10 to the 7. So this one will go from 10 to the 7 all the way to 10 to the 9. Then we have a few more, and all of these sort of have their specifics on when you use them. This one's good for this range here. I'm just summarizing these here. This one is a transitional one. I'll highlight them on the plot in a second here. 10 to the 9. So when you're seeing these references to these equations, we have the laminar is this one here. So we notice what the plot is. That's a log scale on the Reynolds, and the drag coefficient is plotted here. So that's why this exponential behavior here shows up as a straight line, because Reynolds is on a log plot. We have the turbulent, that's this equation is referring to this one here, that's 934. So that's plotted right there. And then this guy is when you have the higher Reynolds numbers out here. So that's that guy plotted there. And then the transitional one is this guy here, which is 937b. That's that transitional one right there. And so as per usual, it's really important we stop and really dissect this plot. So drag coefficients, we remember that's just a dimensionless drag force, right? So the smaller that is, the smaller the drag force is, essentially. So when you look at laminar, basically a few things we note on this laminar curve right here is that the drag force is lower, right? Remember, this is purely friction drag, right? So shear drag, purely friction drag, laminar boundary layer will have less drag than the turbulent layer does, purely in the friction sense, right? And as the Reynolds number increases, this drag is seen to decrease as well. Then the transition's shown here, and it's a little bit funny, right? Because as I mentioned, the transition can sort of be, so that's showing like 5 times 10 to the 5 here, and then all the way out, like this is a Reynolds number of 10 to the 7. So the transition is sort of shown as like possibly at about 5 times 10 to the 5, but that can vary as well. So then if you do have a transition, you follow this curve, right, which then becomes a function of the Reynolds number as well if you're in the transition zone. Then once you get to turbulence, you're following these two lines here, right, this equation and this equation we talked about above. And again, you note just purely when you're talking about friction drag, turbulent boundary layers have higher, and it's fairly considerable, right? Much higher drag in a turbulent boundary layer for the friction forces. And again, that can be seen to decrease. So this is going as Reynolds number goes up, right? We're seeing a drop here, a decrease in the friction as well. So higher Reynolds number causing a drop in the drag coefficient. And so how do you study for this? What do we care about? What's important to know about a section like this? You really need to be able to look at a plot like that and understand, what the drag force behavior is, and then how are you as a designer going to take advantage of that? So if you want the smallest friction drag you have, there's a few things you can do. You can increase the Reynolds number, or you can switch the flow from being turbulent to laminar. In some cases, that can be done by just making the plate very smooth. So a rougher plate is going to trip to turbulence quicker generally than a smoother plate will, right? So these are the types of things, this really deeply understanding what is going on here, especially in a plot like this. That's what we want. That's what's going to make us good engineers and good designers. Okay, that was pure friction drag. We're going to go here to pure pressure drag. So in this case, you basically rotate the plate exactly this 90 degrees here. So now your plate looks like this in the figure. Now we say there's zero friction drag in a case like this. And we say instead it's all pressure drag. So now we write the drag force like this. All the drag force is going to be the pressure forces, right? So the normal forces along the surface. And I want to play a video. Okay, not the best video ever, but we can see the difference between the laminar wake and the turbulent wake. So we see our flat plate there and the flow flowing over it, and how we're going to have just the normal forces here in both cases. So that's a demonstration of what we mean by having a flat plate normal to the flow. Okay, so one thing about, in considering that video and also the car one we just saw, is that when we say drag, so the drag force in this case is like parallel to the flow, and so it's all the forces that are pulling back that way, right? If we're gonna be directional about it. That's our drag force. So oftentimes when we have, for example, when we put a car in a wind tunnel and we pass the air over it, we're just simulating what happens on the road. Right, so if you had a little car like this, I'll draw, a super generic car here, and you have the wind tunnel coming like this, that's just simulating the fact that on the road, this car would actually be driving. And so any drag forces, again, on that car are pulling back in this direction, right? So when you're looking at a flat plate like this, you're gonna have the influence of the pressure force. So you have basically the pressure force pushing here from the velocities that are hitting the plate there, right? So because this velocity is hitting the plate there, and we know there's a dynamic pressure as well, you're gonna have a higher pressure here pushing on the plate, and that's in this drag force direction, right? But then in this wake zone here behind the plate, you're also having the influence of the fact that you have this turbulent air back here. And what tends to happen in these wake zones is you have a lower pressure. So that's called the wake pressure sometimes. There's a lot of different names given to that, but that lower pressure back there is also going to cause a corresponding force in the drag direction here that pulls back on that plate. So we could think of, like, same as the car, we could think of, well, rather than having a plate just sitting here with air flowing over it, you could also think about, what if you had this plate and you were trying to accelerate it forward? Right? So if you were trying to move this plate forward, then you'd have the same kind of thing where you'd have this net result of this air passing over it. And then this drag force would be resisting you from trying to move that plate. Or if this plate, for example, was facing the wind and you needed to mount it in place, this kind of drag force would be pulling back on it. So you'd need to make sure you can counterbalance that pressure drag that's caused by the airflow that's flowing normal to this flat plate. Okay, so we look at this again. We've seen this from before. Most of these are experimental. So again, we're plotting drag coefficient. And in this case, it's aspect ratio. So now you're looking at the frontal area of this plate. We're basically seeing the drag coefficient increase a little bit as the aspect ratio goes up. So that's the relative distance of this B to this H. As that increases, you're getting a little bit more drag force there. We also can look at very specific shapes to see how the drag force changes versus these objects. So again, you have this square prism, and there's two different drag force values there, depending on how wide the rectangle is versus how deep back it goes, where they're showing the flow directions in these, right? You've got a disc and a ring, where a ring has a little bit higher drag force. You've got the hemisphere with the flat side facing it. Now that has a higher drag coefficient, as we would expect, than the more streamlined design, right, of when you have the hemisphere part facing the flow, right? That's only 0.3. It's much less, much more aerodynamic, right? Same thing for a C-section, right? So that is going to have much more drag, 2.3, almost double, right? Versus if you have the C-section facing the wind itself, much lower drag coefficient. So there's all sorts of tables like this to help you get the drag force. And again, that's something that is generally measured experimentally. So something you could do yourself if you had a really unique geometry. And one other thing to note here, the reason they're showing these plots saying Reynolds are generally greater than 1,000, that's because when the Reynolds is beyond about 1,000, it doesn't matter anymore what the Reynolds number is. So you find very much the same drag coefficient regardless of the increase in the Reynolds number. So that's just saying, you know, this is pretty much true anytime you're above 1,000, which is a fairly low Reynolds number for these situations, right? So anytime you're above about 1,000, you're just going to have the same drag coefficient. It won't change anymore with the Reynolds number. And so that's why you see it plotted there, right? Reynolds greater than and equal to 1,000. Okay, now we're going to look at a section called friction and pressure drag, where we look at both of those effects together, because many objects we're going to be concerned with when we're looking at the fluid forces and their influence on these objects, they're going to have components both of friction and pressure drag. And just a quick note here, when we looked at friction drag, one thing we saw is that it depends on the Reynolds number quite a bit. So we had that plot there where the CD, so the drag coefficients, were plotted as a function of Reynolds number. Then we came across pressure drag, and you'll remember in that section there was no Reynolds dependence. And so those tables, for example, that we were looking at, they just kind of said, you know, when Reynolds is greater than 1,000, your CD is just going to be this value. So that's one thing we sort of want to keep in mind as we're marching through this section. So I mentioned the vast majority of this stuff is done experimentally, right? Because in essence, what we have is sort of section 5, like playing itself out here, right? So we've non-dimensionalized, you know, our drag force and found out that it's a function of the Reynolds number, right? So we only have now these two parameters, right? So the drag coefficient and the Reynolds number. And so a whole bunch of experiments can be run and this can be plotted. So the plot we've got here, one of the best ways to look at the influence of both friction and pressure drag is to consider this smooth sphere, like our go-to example in this class, right? So this plot is for a smooth sphere. And we're going to notice a few things first of all. So at low Reynolds number flows, you remember when you're really low Reynolds number, your viscous forces are actually completely dominant. And this is also called Stokes flow. So this theorem that Stokes came up with applies down here at these really low Reynolds numbers. So that's a log scale showing times 10 to the minus 1, right? So Reynolds number is basically less than 1 at this point. And he showed the drag force expression listed there. It's a function, a linear function with the velocity here. And he found the drag coefficient is roughly 24 over the Reynolds number. So what we see when drag coefficient is plotted, you've got this dashed line here, you know, that extends across this data. So you see it's very representative up until about this point here. So below a Reynolds number of about 1, the Stokes data predicts the drag coefficients very precisely. And then it fails to do so beyond that point. And that's because up here, you mostly have friction effects. Very viscous, very laminar flows, right? Then as the Reynolds number increases, you're starting to add the influence of pressure drag and you're getting wakes. And that's why you're getting, if you look right here, right, you're getting a deviation between Stokes' theory, which is purely viscous flows, and the actual data points. They're starting to deviate there, right? Now, if you keep looking along this curve as Reynolds number increases, you get to about Reynolds of 1,000 here, 10 to the 3, and right around this point, if you sort of look at the curve, right, it's pretty flat. So drag coefficient at that point is pretty constant as Reynolds increases. And at this point, we know from measurements, that's about 95% now is actually pressure drag. So as the Reynolds was increasing, we went from this friction drag all the way down here. And now basically your pressure drag is becoming really dominant out in this section here. And so just a super quick flashback, right? If we look up here again, right, we know, again, so friction, we found pure friction depended on the Reynolds number, but pressure drag did not depend on the Reynolds number. And we're seeing that, you know, again, in looking at this plot, right? So the friction section up here is a function of Reynolds number, and the pressure dominant section down here is not a function of the Reynolds numbers because the CDs are constant, right? So, okay, so now as we follow that curve, we see there's one more really interesting point right here, right? So I'll reiterate once again, because most of this stuff's experimental, the skills that we're developing in this chapter are really related to, understanding equations, understanding these concepts, and also a lot of this is going to be like, can we look at these plots and decipher what's going on? From a design, from an engineering perspective, looking for opportunities to improve our designs, right? If you can read these figures, you have a big advantage. So if we look at that point, I'll actually just pause for a second and see if you can figure that out. So you've been increasing the Reynolds number from Stokes' flow that was very viscous, right? Nicely laminar. Then you increase that Reynolds number higher and higher. Now you're starting to get a situation where you're having a separation point. So you're getting a wake behind the spheres. Now, what do you think is going to happen? What's going to cause this drastic change that I've put this arrow at right here? So that's about, 3 times 10 to the 5, let's say, Reynolds number. So what do you think that could be? You can pause it again and think it through. So what that's representing is actually a transition to a turbulent boundary layer. And the drag coefficient just absolutely drops straight off. We see a massive decrease until eventually, as Reynolds is increased, and remember this is a log scale, so these are now huge Reynolds numbers, you're getting a little bit of an increase in drag as you continue to raise the Reynolds number. But what's dramatic here is the transition point. From laminar to turbulence, it just absolutely drops off a cliff, right? And you're going from like 0.4 down to like less than 0.1. I mean, that's 4 times less drag just across that transition. So it's very dramatic. So let's think about that for a second. So we remember in the friction section that we said that when you transition from laminar to turbulent, actually your drag is increased, right? So in the friction drag section, a transition increases the drag. So what the heck's going on here? How come a transition to a turbulent boundary layer drops the drag? Well, remember, that's because this is pressure dominated though, right? So most of what's going on right here is actually due to the wake, right? So the pressure that's at the front of the ball sphere, the pressure that's at the back of the sphere. And so what is that transition to turbulence really doing? Well, we remember when we talked about separation. So the separation points are what's generating the wake, right? And the size of the wake is what is determining the pressure, that low pressure region that's pulling back against the sphere. So transitioning to turbulence, a turbulent boundary layer is capable of fighting or resisting that separation for longer, right? Because it has better momentum. You remember we talked about that. So the transition to turbulence, then the turbulent boundary layer is capable of delaying separation farther along the back of the sphere. So I'll draw a sphere here, right? So if a laminar is having separation, say up here, right? Then you're getting a wake that might look like that. And if you can delay that transition point, if a turbulent can be somewhere back here, I'll show you a video in a second, and generate a smaller wake by delaying that separation point. Now this pressure region, see there's only a tiny area acting over the ball versus this gigantic wake that's acting over this whole surface back here. So I'll pull up a video here. I think it's going to demonstrate this a little more clearly. Okay, so I'll hit play here and then use the cursor. We'll look at the one on the bottom first. So the laminar boundary layer, you see the separation points are roughly at the top and bottom of the ball, and you get a huge laminar wake here. And the turbulent, its separation is much smaller down here, so you're getting a much smaller wake behind the ball. So because your pressure drag dominated at that point, you're going to have a lot less pressure drag on the sphere with turbulence versus the sphere with the laminar boundary layer. Okay, now we'll look at a plot that describes this as well. So I mentioned this is experimental in nature often. So this plot helps us understand exactly what we just saw with some data here so we can understand it. So what's being plotted here is actually this pressure coefficient. We looked at pressure coefficients in section 5. They were one of the common dimensionless groupings that we came across. So you can think of this pressure coefficient as really just looking at, like it's looking at the surface pressure, and then it's dimensionalized against the dynamic pressure of the flow. And we're plotting against theta, right? So that's shown in this picture right here. So we can think of our stagnation point right there as having this maximum pressure, right? All of it's converted from the dynamic pressure. And then we know as this air flows over the ball, right? We can think of it, let me just erase this so I can more cleanly draw on this picture. It's going to be really important. So you can think of like the free stream flow is up here, and then you basically have this angle like this that's squeezing the flow down. then it's flat for a brief moment, and then along the backside, it's expanding. So as the flow is coming over the top like this, you're sort of forcing it to squeeze down, as we saw over the airfoil, right? So the velocity is increasing at this point, trying to squeeze through that smaller area to get around the ball. And so as V goes up, we expect P to go down, and that's shown on this plot, right? So P drops way down. Now, we've got two different curves, so let's focus on the laminar one first. So here we go, the pressure's dropping, and we watch this angle, so at about 90 degrees there, just before 90, so let's say right here, we have a continual drop in the pressure. Now, I've drawn this angle like right here. Now, as the air reaches that peak point at 90 degrees, now it turns back down, and now it has a larger area to fill. So if I trace this in sort of like green here, if you just sort of look at the free stream flow and this angle and this angle, this angle, you can see it looks a lot like that duct we were talking about before, where you're starting with like a bigger area here, and then you have a smaller area right at the 90 degrees, and then you're sort of moving out to a bigger area again. So I'll clean this up yet again so you can see my arrows here. So as the flow comes around the back, right now, velocity is going to be slowing down, therefore pressure is going to be going back up. So we see that the pressure starts to increase here. Now, there's a drastic change there in the plot. So let's think about this for a second. And remember, we talked about favorable and adverse pressure gradients, right? So the favorable ones are when you have a high pressure and you're going to a low pressure. So again, another color. So all the way as the flow is flowing around the ball, you're going high pressure to a low pressure right until right there. So that's favorable, right? Okay, then adverse, right, is when you're going from a low pressure to a high pressure. So now on the plot, you see the moment you sort of turn that corner, now your pressure is going back up. Well, this little S here is denoting separation, right? So I'll clean this up again because this is a really critical point. So you notice this is laminar, right? So that's a very smooth sphere. So the moment the pressure starts to pick up, you see that laminar boundary layer is actually terrible, right, at fighting back against separation. So basically the moment you have an adverse pressure gradient, you separate, and now you can see, I mean, there's a little bit of drift there, but basically the pressure's constant. And it stays constant at the point where separation occurs. That's roughly the behavior you see in the wake there, right? And that separation, if we go down and look at where that's occurring, that's roughly at 90 degrees. So again, I'll look at the golf ball for a second. If the flow is there, you have separation right there. If it's laminar flow, you know that's going to create a huge wake behind the sphere, like the one we saw, exactly like the one we saw in the video, in fact. Now, if you're turbulent, I'll use purple for this. Okay, so turbulent, you're traveling over the sphere, right? So you're right here at first at the stagnation point. Now the same exact thing's gonna happen, right? Velocity slows up, you're following this curve down here, and then you're gonna get the same thing. You basically reach that top point on the sphere at 90 degrees. So now your pressure is going to climb back up as the velocity slows, but you're turbulent, and turbulent boundary layers can resist separation. So the turbulent boundary layer is able to form all the way along the ball until right about here. That's its separation point. So you see it got way farther along. If I can sort of attempt to draw a straight line, somewhere in the ballpark of 140. So if this is 90, now you're talking about, sort of way back here, you're going to start to have your separation. So your wake is this purple zone instead of the blue zone on the golf ball there. And then again, what's really key is like, not only is your zone smaller, but you see the pressure stays roughly the same in the wake as it was at the point where it separated. So you're comparing now, the green is the pressure basically that the front of the ball is feeling, right? So that's your stagnation point. So that's your pressure there, pushing back against the ball, like right here. And then, so not only in the laminar situation, this pressure behind the ball is huge. It's this whole zone right here. Not only is it bigger, but see the pressure is lower, right? Because that pressure is lower than it is in the turbulent layer, whereas the turbulent layer, it's not only smaller, right? So this purple right here, if you can still see those scribbles near the golf ball right there, the purple is not only smaller, but you see the pressure has climbed a little higher, right? So that P is a little higher. And a quick reminder of how these pressure forces contribute to drag. So the high pressure at the front, right, resists the ball from moving forward, and a low pressure at the back creates, we can think of like a suction that's pulling back against the ball. So the difference between the high pressure at the front, low pressure at the back results in a force that's pushing back against the ball. So this explains why, right, in the turbulent case, you have a much smaller wake and you have a higher pressure in your wake. Therefore, that's why you see that drag coefficient drop by, a factor of 4, right? It's gigantic because it's way better once you're dominated by pressure drag. It's way better to have a turbulent boundary layer. And really listen to what's being said there, right? And make sure, so you're jotting down your notes now, right? This is really sinking in because this is so important, is that I'm always clarifying, like I said there, when you're pressure drag dominated, that's when you would want turbulent flow, right? Because we know if your friction drag is dominant, you definitely prefer laminar flow because the turbulent flows cause more friction drag. But in this case, your turbulent boundary layer might be causing a little bit more friction drag. We know that, but the pressure drag is what's causing, roughly 95% or at least 95% of your total drag is just the pressure drag, as our plot showed above. So you're so pressure drag dominated that the turbulent effects, because they influence the pressure drag so dramatically, the net gain is that you have way less drag. Even though you might have a smidge more friction drag, just friction drag doesn't matter in this case. You're pressure drag dominated. Okay, now this I think is going to help us explain why you would dimple a golf ball. See, it wouldn't make any sense if your golf ball here was, friction drag dominated. Making it rougher wouldn't make any sense. You'd increase the drag. But because your golf ball is at a high Reynolds number, then the sooner you get it to transition to turbulence, the less drag you're going to have on it, meaning it's going to travel much faster. And what you can do, you see this point is like 3 times 10 to the 5 that I highlighted where this drop is. If you roughen the ball though, they've shown that roughly right around here, so even as low as say like 50,000-ish, you can get a transition to turbulence actually occur faster. So through much more of the golf ball's flight, right, you're going to have that lower drag. You're going to have that transition occur earlier if it's rougher, because the rougher surface is there, more likely to trip into turbulence. Now, baseball is really interesting too. So we'll talk about only one kind of pitch here because we're going to look at spin. Spin is very critical for baseball pitches. But there's one kind of pitch where you try to minimize the spin as much as possible. That's a knuckleball. So let me try to pull up like a slow motion knuckleball pitch so everybody can have an idea of what we're talking about here. Okay, so I found this YouTube video here. Let me click play and watch this. It's going to show his knuckleball in slow motion. So a few of the things we're looking for, if I just have the cursor, look at how that thing moves. The catcher himself, even who's trying to catch this ball, has no idea where it's going, right? That ball is just all over the place, and you can see it has very little spin on it. Watch it again. Very little spin, very little, some but very little, right? And just watch that thing. It's just dancing, right? It's all over the place. It's so hard to hit a really well-thrown knuckleball. Oh, that's incredible. Okay, so what is going on there? So we'll talk about spin later, but the knuckleball is thrown with very, very, very little spin. So here's a picture of a baseball in the bottom left here, right? And what happens is if you can throw this ball with very little spin, then you'll notice these stitches, right? I'll highlight the stitches right here. There's these stitches on the ball. So the ball is very smooth except for these stitches. So what can happen is you have these really localized points of roughness. Like the stitches are creating this zone of roughness only in one tiny little spot on the ball. So as the ball, you saw when he threw that ball, it moved a tiny little bit, right? So that was R.A. Dickey pitching, and they had slowed those pitches down, right? So we could see that. So what we could see when that ball was moving, right, was that it was dancing all over the place, because if you throw it with no spin, anytime the air hits a stitch, it roughens, and so it has turbulence at that one little spot. And so because only the tiny little spots where the stitches are located have turbulence and the rest of the ball is smooth, so the rest of the ball is laminar, you get this crazy effect where the forces on the ball change dramatically because the drag forces in one location are more or less than the other, causing the ball to just dance all over the place, right? So you can see there very dramatically the fluid forces change drastically because of those localized pressure effects on the ball when you're switching between laminar and turbulence and the drag effects, and it's just pulling the ball basically all over the place, right? It's kind of an incredible representation of what we're looking at. Okay, so let's march forward to something else we want to look at. So that's called streamlining. So streamlining is the idea here that as engineers, we want to make something that has as little drag as possible. So I'll draw like a sphere up here, and you can also think, so there's some data for cylinders that's very similar to a sphere, so I didn't show that as well, but we can think of this as like a cross section of a cylinder. And the problem is because, as the fluid flows around this, there's a very dramatic change in area after you hit the top of the ball as the flow comes down the backside, right? This very dramatic change makes separation possible. It's very hard for the air to stay close to the ball, to stay attached, or cylinder, I should say, to stay attached when you have that dramatic change. So you look at these streamline shapes or these airfoil shapes, a lot of what they're trying to do is just at that peak point, you just try to be as gentle as possible. So you try to just extend this out as long as you possibly can so you don't get that dramatic change as the air comes around that corner, right? The more gentle it is, the less likely you are to have the drastic change in pressure. Therefore, you're likely to keep the flow attached for longer. So that's the idea in streamlining. But of course, you're limited because ideally you'd want this to be as gradual as possible. From here, you just go back and back and back. The farther you can go back, the more gradual you can be. But the challenge there is that the longer you make that, so the farther back you go, if you keep extending this farther and farther back, you're actually also increasing the surface area. So here's a plot showing, thickness versus chord length, right? So thickness, let me just erase this so it's more clear. So thickness is the T variable there. So like 0.5, it means that like thickness is about half what the chord length is. So that's about twice as long. So you're getting a shape that looks like basically like that. And then the smaller and smaller your thickness is as compared to your chord length, you're getting shapes down in this end of the plot where you're getting like much more gradual shapes. So now your thickness is much smaller in comparison to your chord length, right? Which is like much longer. So in these shapes out here, in this side of the plot, we know the problem there is we're very pressure drag dominated. So this curve is pressure drag here. So you can see out here high pressure drag, and then skin friction drag though is a little lower because you don't have as much surface area. So that's skin friction drag there. Whereas if you're able to lengthen that, so you move down this way, right? And as you move that way, you can see your pressure drag is starting to drop because you're not getting a huge wake anymore, but your skin friction drag, if we follow this curve as well, is going that way. It's going up because you're getting a bigger surface area, right? So when you plot total drag, you see there's sort of this optimal point where you have a trade-off between friction drag and pressure drag. So that's why you don't see these shapes extended really far too often, because what you're looking for is that thickness over chord length that's, approximately like 0.25 out here just for this case. Remember, these are experiments, they differ. These are just representative cases, right? But you kind of want to be where that total drag is minimized. So you want an aerodynamic shape where you're streamlining, but you're not increasing the friction drag by too much. Okay, and as we march through this, again, you'll continue to see the importance of like all the figures we're drawing and all the plots. That's really what the emphasis of section 7 is. So if we look down, there's another way we can describe this. So a very important variable is the location of max thickness, so shown here by this like T max representation. So if you look at a conventional airfoil, it'll be pretty far forward. So T max is sort of roughly around here. And then you have a laminar airfoil where the thickness point, the thickest point is like moved back, down around here. So they move the thickest point back. So, the location of the thickest point, so if the thickest point is like maybe here in this case, and it's maybe around here in this case, what happens is you're looking at this distance, so x, along the airfoil, and again, we're mapping out the pressures. Pressures, of course, are, as we described earlier, that's what dictates the separation, right? It's the adverse pressure gradient that's causing separation. Okay, so we follow the plot on the conventional airfoil, which is this guy right here. You follow that down and you see, okay, right there, you're starting to get adverse pressure gradient. So you're going from a low pressure to a high pressure now. And that happens very early on in the section, right? Because the thickest point is much sooner. And so to try to delay separation in a lot of these cases, now that you have this adverse pressure gradient, you'd be more likely to want turbulence along that surface. But turbulence is great in delaying the separation point, but it's bad, right, for friction drag. So you see what ends up happening is when you sort of look at all these effects, now you've got turbulence to try to prevent the separation, and you're getting a drag coefficient roughly 0.0061. Whereas in the laminar flow section, right, I'll trace this one in purple so it's more clear. So you're following similar curve, but then you've pushed the thickest point back. It's following this curve here, coming down here, and you don't get that adverse pressure gradient until way back along the flow. So that's because the thickest point's back here. So now you get adverse pressure gradient only about this point, so you can keep a laminar airfoil much smoother along much more of its surface. And so you see what happens is the net resulting drag coefficient is actually quite a bit lower, right? So there's a lot of very clever things you can do when designing airfoils in terms of like understanding pressure drag and friction drag, right? And all the different things that are under your control, because now that you know the basic physics, right? And the basic physics tells you once the pressure has to turn that corner and go down the backside of the cylinder or the backside of the airfoil or the backside of the sphere, once it's headed down the backside, now you're gonna get an adverse pressure gradient, right? So a few ideas we've talked about right now is extending the shape so you don't make it as dramatic of a drop off on the backside, right? Or you can change the location of the thickest point, right? So you literally change where that adverse pressure gradient starts to form, right? It lets you stay laminar for longer, knowing that a laminar flow has less friction drag, right? So you see the key concepts coming together in these designs here and why this chapter is so conceptual. There's a lot of different ways we look at this, a lot of different experiments that have been run. This one shape shown here before we move on to the next section was optimized because now that we have greater computing power, because we rely on experiments to do a lot of this work, it can be tedious, right? It can be cumbersome to run experiments for everything. So if we can supplement that with some high-powered, computational predictions, then you start to get shapes that look a little more like this, the classic teardrop shape there. And then you can run experiments knowing kind of what these optimized shapes will be. You can then plug those into your wind tunnel, take some measurements, and the pairing, between the computational analysis and the experimental analysis can lead to some much more creative or innovative designs. And you'll see, for example, like on some really high-end bikes, they'll have this kind of shape for all the posts that are facing the wind. Some cars, right, if you look closely at the antenna, for example, if they're really serious about reducing drag, you can actually have different shapes for the antenna or the struts of the vehicles themselves. So there's lots of situations. Oh, aircraft too. Aircraft too, when they have struts, for example, on their landing gears and stuff like that, they'll also make those aerodynamic shapes to reduce the drag as much as you possibly can, right? Anytime you have sort of a cylindrical shape like that that's facing a flow, you're really gonna wanna make sure the drag is reduced. All right, so now we're gonna move on to a few more of these practical examples of how we use the drag coefficient and how it's changed. You remember the video of the cars? And we can see now that we understand a little bit more about these drag coefficients, you see the gigantic wake behind this older car, and the Streamline car has a much smaller wake right here. And of course, we know there's friction drag effects too along the vehicle. We'll talk a lot about that in the upcoming lecture, right? And so you've got this dual influence of like the pressure drag and the friction drag. Okay, so we also have a plot of that where you're seeing, drag coefficients plotted here. And as you have the cars move from the older cars to the more newer cars where they're more streamlined, you're getting a pretty dramatic drop in the drag coefficients. And this is shown for time right here where we're able to reduce those drag coefficients. And just recently, there's been a few very large gains in reduction in drag coefficients, partly because of the electric vehicles now that want to have a longer range for an individual charge on their batteries, right? So one of the strategies they've employed is like if you can reduce the drag coefficient, then you can reduce the amount of power that's required to make the vehicle move, right? So fuel savings or longer distance per charge for your battery, that's caused the drag coefficients to drop again. And there's another neat plot here, and you can see like cyclists, this is really kind of a fun thing to look at. So the upright commuter bike drag coefficient, if we baseline at sort of 1.1 there, when you're racing or you're in a tuck position, right? You drop that a little bit, 0.88. If you're drafting because the person in front of you is responsible for upsetting that airstream, the airstream can pass over the second racer in a much different way. So that racer is actually pulling in behind the wake of the person in front of them. And so you drop that drag coefficient dramatically, right? If you've ever felt that, it's really dramatic when you're drafting somebody. You're using so much less power when you're cycling. And then streamlined vehicles, I have a friend who really loves these streamlined vehicles. So the one where you're kind of seated down and your knees are a little higher has a hugely reduced drag coefficient. So much less power is required to get those things to move quickly. So we look at tractor trailer trucks, and you probably noticed this on the highway now. There's actually, because there's a cost incentive, right? So if they can reduce their drag and reduce the fuel that's required to move the cargo, they can reduce their cost dramatically, especially when fuel costs are so high, right? So you look at a few changes here. If the standard's 0.96, you get it down to 0.7. just by putting this little gap seal here. Now, you've also might have noticed more recent changes they've got underneath here. They've got those flaps, and some trucks even have support at the back, right? So they're trying to make this more gradual at the back here too, what I'm drawing here, and a more gradual change behind the tires. So all of that, as the price of fuel rises, right, those changes become very useful, very large cost savings in that. And we know why, right? We know the fundamentals now. So you could, for example, if you're working for them, you can suggest these changes and test them out in a wind tunnel and with a model truck, and you're good to go, right? So lots of fun actually in designing these things. They've shown a tree, a dolphin, large birds. I guess those are fun to compare as well. But yeah, there's lots of different shapes, lots of different objects that are important in the wind, right? Or traveling at certain speeds. Okay, so that's all for drag, and we'll stop there. Now, a quick summary of video number 20 here. We looked at the different types of drag force you can have, right? We looked at a pure friction drag, a pure pressure drag, and then we looked at both friction drag and pressure drag. And so when you look at them together, there's sort of an interesting interplay. You have a change in the behavior when the flow behavior changes. So for example, as the Reynolds number increases, you move from flows that are friction dominated, so where the drag is mostly friction based, and then as the Reynolds number increases, we saw this for spheres, you actually get a pressure based drag. And we saw in particular that makes a big difference in where you have a laminar boundary layer and a turbulent boundary layer. In cases where your pressure drag dominated, we saw switching to a turbulent boundary layer actually decrease the drag considerably. So we talked about spheres. Cylinders were very similar. So we didn't talk about them independently, but we did look at strategies for streamlining. And the idea in streamlining is you try to take a more gradual approach on the rear of the object so you don't create as strong of a wake or as defined of a wake. But then, of course, you sacrifice in friction drag as well. So we went through a lot of these plots and really trying to understand the relationship between the friction and the pressure drag. We looked at how cars have come a long way and how the different types of drag influence on different types of bicycle configurations as well. Okay, now as a follow-on to this video, it's going to be 2 examples. I'll calculate the drag on a vehicle, and then I'll look at the terminal velocity of a raindrop, which I think is a really fascinating example of how drag forces are balancing gravity forces in that case. So I'll put those 2 videos as separate videos after this one. And that's all for video number 20.
Bye-bye.